In Chapter 4, we're going to talk about solutions. Solutions play a very important role in chemistry. An enormous number of chemical reactions take place in solution. We're going to start by defining what we mean by solution, and we're going to focus on that in this talk. And later on in this chapter, we'll talk about important categories of solution reactions, including metathesis reactions, which form precipitates, and acid-base reactions, which again play a very prominent role in chemistry and are extremely important to understand in a variety of other applications, including biology and geology. So let's start in section 1 with definitions. A solution is just a homogeneous mixture. That's it. That's the entire definition of a solution. Any mixture that is homogeneous is a solution. So for example, air is a solution of homogeneous mixture of gases. Salt water is an example of a solid mixed with a liquid to form a solution. We can dissolve gases in liquids like carbonated water. That's a solution. We can actually dissolve hydrogen in platinum. That's the solution formed by a gas dissolved in a solid. Brass is an example of a solution of two metals. And in fact, brass is just a combination. This is just a photograph of brass. Brass is a mixture of copper and zinc. And finally, we can have liquid-liquid solutions. For example, alcohol dissolves very nicely in water. Now there's 3 parts required to specify a solution. If somebody else wants to use the solution that you did to repeat an experiment, for example, we have to specify 3 parts. One is, what was the solvent? In our course in general chemistry, our most common solvent is going to be just water. That would form aqueous solutions, and that's our most common solution. So we're not going to do a lot of gas-gas solutions in general chemistry. The second part you have to specify is the chemical identity of what it is you're dissolving in your solute. So for example, maybe I have copper 2 nitrate that I want to dissolve in my water. Copper 2 nitrate is a solid, really a pretty royal blue solid. And if I mix them together, I get the resulting solution, which is the homogeneous mixture of the copper 2 nitrate dissolved in the water. And if I want to tell you what solution to use, I have to tell you what the concentration of the solution is. And we're going to talk about units of concentration in section, I can't remember, 3 or 4 of this chapter, but not right now. First, let's address sort of an interesting puzzle involving solutions. Suppose I prepare a solution by dissolving 1 mole of hydrogen chloride in enough water to make a total of 1.0 liters of solution. If I then go into that solution and look for HCl molecules in solution, I'm not going to find any molecules, not a single one, which seems a little confusing at first. It seems like it ought to have some molecules in there, but what happens when this molecule dissolves in water, it interacts with the water, and the water molecules actually pull these 2 atoms apart in such a way that they form ions in solution. So HCl ionizes 100% in water to form hydrogen ion and chloride ion, and I can't emphasize strongly enough, it breaks apart into ions, not atoms. So it's really important to show the charges on those species, H+ ion and chloride ion, not hydrogen atom and chlorine atom. If it helps to remember this, this is sort of like the difference between sticking your fingers into a lamp socket with the light turned off when it's uncharged and sticking your finger into a light socket when the light is turned on. I assure you the experience will be very different. So it's important to maintain the difference between charged and uncharged species. So solutes whose aqueous solutions contain ions are called electrolytes. That's the definition of an electrolyte, a substance which when dissolved in water, it forms ions. Electrolytes conduct electricity in solution. That's one of the important features of electrolyte solutions. So here I have some examples of electrolytes: potassium nitrate, sodium chloride, hydrochloric acid, acetic acid, ammonia, calcium hydroxide, and there's many, many more, and we're going to look at how to classify substances momentarily. As non-electrolytes, things that do not break apart into ions at all in solution, we would include water. Water itself does not break apart into ions. Water is a very, very poor conductor of electricity when it is pure. When I say this, I always tell students that doesn't mean you should sit in a bathtub of water and throw in a plugged-in toaster. I assure you, tap water conducts electricity just fine. That's because tap water has a lot of ions in it. It's not pure water. Sugars don't break apart into ions. Alcohols don't break into ions. And in fact, most molecules don't break into ions. There are some exceptions, of course. As we see here, these are all molecular substances that do form ions in solution, and I'm going to give you some guidelines to tell when molecules will form ions or not. So the electrolytes themselves can be classified into two categories. We call them strong electrolytes if they exist entirely as ions in aqueous solution. That is, there are no substances that don't break apart into ions. And we call them weak electrolytes if they only partially break apart into ions in aqueous solution. As examples, hydrochloric acid is a strong electrolyte. It breaks apart 100% in solution into hydrogen ion and chloride ion. Again, charge is super important. Remember the light socket bit. Acetic acid only partially breaks apart into ions. We show that this reaction goes in both directions with this double arrow, one arrow going forward, meaning some of these molecules will break apart into ions, but in solution, these ions can recombine and go back the other way and reform the molecule. In fact, acetic acid, only about 5% of the molecules break apart into ions in aqueous solution. The rest remain as intact molecules floating around in solution. Now, all ionic substances are strong electrolytes, but only molecular electrolytes can be weak. Only molecular electrolytes can be. They're not necessarily weak, but they can be weak, and we'll see how to predict that in just a moment. Okay. Now, some points of clarification here. Acetic acid is very soluble. A lot of it will dissolve in water, but no matter how much dissolves, only a small fraction of it breaks apart into ions. That's what makes it a weak electrolyte. In contrast to that, barium hydroxide, not very much of it will dissolve, so if you throw a handful of it into a cup of water, most of it's going to sit at the bottom as a solid, undissolved. But the amount of it, the small fraction of it that does dissolve, will break apart 100% into ions, and that's what makes it a strong electrolyte. So being a strong electrolyte does not guarantee solubility. Now let's see how we can identify compounds as being electrolytes or non-electrolytes. There's three common electrolyte types that you should know about. The first are acids. Anything that is an acid, by definition, acids form hydrogen ions in aqueous solution. By the way, we often call them proton donors because if you think about this, a hydrogen atom consists of one proton and one electron. So if you take the electron away to leave an H+ ion, that ion is actually a proton. It's literally a proton. So acids we think of as proton donors, and that's one class of electrolytes. A second class of electrolytes are bases. Bases can be thought of as the opposite of acids. In some sense, they are proton acceptors. These are compounds that form hydroxide ions in aqueous solution. And we can think of the proton that's being donated by an acid could react with an OH ion to form a molecule of water. In that sense, they react with acids. The third category are salts, and these are simply non-hydroxide ionic substances. And this is it. Those are the three types of common electrolytes. So let's see some examples. Here's some example acids: nitric acid, hydrochloric, hydrocyanic, hydrofluoric, sulfuric acid. Some bases, most of which contain hydroxide: potassium hydroxide, sodium hydroxide, calcium hydroxide. Ammonia is the one molecular base that you need to know about now, and it is a weak electrolyte. All of our other bases are going to have hydroxide in the formula. And then if you mix acids and bases, they actually form salts. So think about the relationship between the formulas in a column in my table of examples here. Now let's see what happens in solution. So strong electrolytes exist in solution entirely as separate ions. So for example, in solution, if I dissolve potassium nitrate in water, you should think of it as a source of potassium ions and nitrate ions. Again, always charged particles when we form electrolyte solutions, always charged particles. Calcium cyanide will break apart into its respective ions, namely a calcium ion and two separate independent cyanide ions, which will float around in solution separately. Now, if I mix strong electrolytes, say I take my solution of potassium nitrate and I mix it with a solution of calcium cyanide, as I'm showing here, then I'm just going to get a mixture of all of those separate ions floating around in solution, with one possible exception, unless some combination of cations and anions from the potential list of ions formed here, if they form an insoluble compound, then a chemical reaction will occur. We call that sort of chemical reaction a metathesis reaction, and that's going to be the subject of our next lecture.